Welcome to the last part of applications of the integral. We will take a look at the notion of arc length, and we will see how the integral can be put to contribution to calculate the length of a curve over an interval AB. So our attention will actually be focused on curves that are differentiable. That means they're continuous and they have no sharp edges or no cusps. So let's consider this graph here of a function f of x over the interval AB. I have partitioned the interval AB into n equal subintervals and labeling my points x0, x1 all the way down to xn. And on the curve, to these points xi correspond a point qi. So for x0, the point q0, for x1, the point q1, and so on and so forth. We have put some random points in the middle here, so to xi minus 1 corresponds qi minus 1, and so on and so forth. So keeping that curve in mind, the idea that we will want to develop is actually simple and quite intuitive. We will approximate the length of the curve on AB by adding the lengths of the line segments that actually join two consecutive points. In other words, the length L of a curve is going to be given by approximately the summation I equals 1 to n of big D of qi minus 1 qi, where that expression, big D of qi minus 1 to qi, simply stands for the distance between the two consecutive points qi minus 1 and qi. You may recall that the distance formula between 2 points, let's call them A, x1, y1, and B, x2, y2, that distance formula was given to be the square root of x2 minus x1 squared plus y2 minus y1 squared. If we apply this formula to our situations, where actually qi minus 1 is the point xi minus 1 comma f of xi minus 1, and qi is the point xi comma f of xi, we get that the distance is the big square root of xi minus 1 squared plus f of xi minus f of xi minus 1 all squared. For simplicity, let's call this equation 1. You may also recall a result from Calculus 1 called the mean value theorem for derivatives. It goes like this. Given a continuous function that is also differentiable on the closed interval AB, we have that there exists a number c on AB such that f prime of that number c is equal to f of b minus f of a over b minus a. Applying this result on f of x on the interval xi minus 1 to xi, we get that f prime of some number w1 is actually equal to f of xi minus f of xi minus 1 over xi minus 1, where wi is just a point between xi minus 1 and xi. So we can actually rewrite this by bringing the xi minus 1 to the other side, and we have something that I'd like to call equation 2. So this is our equation 2 right here. Now, as we actually often do in math, to move ahead, we combine different things that we know. So we're going to combine here equation 2 and equation 1 by putting one inside the other. So we have a big D from my equation 1 is now equal to the square root of xi minus 1 squared plus the square of f prime of wi times xi minus 1. For simplicity, why don't we let xi minus 1 to be equal to delta xi? So what are we going to get here? We're going to get that distance is the square root of delta xi squared plus f prime of wi times delta xi all squared. Let us bring in the square inside to both. So we have a square to f prime of wi and a square to delta xi. Notice that we have delta xi squared here and delta xi here squared here as well. We're going to take it out and we're going to get this. So I have delta xi all squared that is factored out. Since this is a multiplication times the bracket, I can actually take out the square root of delta xi squared, which is delta xi. So at this point in time, we have that L, the length of the curve, is approximately given by the summation I equals 1 to n of the distance from qi minus 1 to qi, which is the summation I equals 1 to n of the root of 1 plus f prime of wi all squared times delta xi. As we are now used to, we are going to let delta xi go to 0, which is equivalent to letting n go to infinity, where n is the number of subintervals on the closed interval AB. And we are going to get that L is actually the limit as n goes to infinity of the summation of the root of 1 plus f prime of wi squared times delta xi. Now, you may remember that wi was just a number in the interval xi minus 1 to xi. On a real line, that means that wi is actually trapped between xi minus 1 and xi. So what happens when delta xi goes to 0? Well, it means that the interval here between xi and xi minus 1 shrinks to be almost nothing. That means that wi is actually pushed upon xi in a squeeze theorem kind of way, and then basically we can replace wi with xi, hence getting L equal to the limit as n goes to infinity of the summation I equals 1 to n of the square root of 1 plus f prime of xi, this time all squared, times delta xi, which of course turns into the integral a to b of the root of 1 plus f prime of x all squared dx. That's the formula we're going to use for the length of the arc of a curve between the points AF of A and BF of B. As an example, let us find the length of the curve of the graph of f of x is equal to 5 minus the square root of x cubed between the points 1, 4 and 4 comma minus 3. So we're going to use our formula. The length of the curve is the integral from a to b of the root of 1 plus f prime squared dx. We're going to put in f of x, which is 5 minus the root of x cubed. We're going to derive x to the 3/2, and we're going to get 3/2 x to the 1/2. Squaring this, we actually get 1 plus 9 over 4x in the square root, with the integral going from 1 to 4. So now we have to evaluate that integral. We're going to take a little quick aside here, and we're going to do a substitution where u is 1 plus 9 over 4x. The du is 9/4 dx. We replace, and we actually get that this integral is equal to 8 over 27 times 1 plus 9 over 4x to the power of 3/2. Putting this back into the FTC Part 2 situation where the bounds are 1 and 4, we do the replacement, and we get this not so nice expression, which has the following decimal answer, 7.63 units. One more example here. This time let us consider the length of the arc of the graph of y is equal to x4 over 16 plus 1 over 2x squared on the interval 1, 2. First, as usual, we find y prime or f prime. So deriving x4 over 16 plus 1 over 2x2, we actually can take out the constants, bring up the x squared on top, it's x to the minus 2. We derive x4, we get 4x3. We derive x to the minus 2, we get minus 2x3. We bring down our negative exponents and we simplify our fractions. The derivative of this is simply x3 over 4 minus 1 over x3. So we put that into our formula. So we get the integral from 1 to 2 of 1 plus the derivative squared. So 1 plus x3 over 4 minus 1 over x3 all squared dx. So we expand this bracket and we get this. We remove the brackets, we collect 1 minus a half, and we're going to get positive 1/2. And here's the tricky thing. x6 over 16 plus a half plus 1 over x6 is actually a perfect square. You can see that by taking the square root of x6 over 16, which is x3 over 4, and taking the square root of 1 over x6, which is 1 over x3, and the double product will actually give you exactly what we have over there. So that being a perfect square, it's perfectly convenient because now we got the square inside the square root, so both cancel out, and we have a relatively easy integral to evaluate. That is the integral from 1 to 2 of x3 over 4 plus 1 over x cubed. So that integral actually gives us a quarter x4 over 4 plus, well, the integral of x to the minus 3 is minus 1/2 times 1 over x squared. The bounds are 1 to 2. Plug in the upper bound, plug in the lower bound, you get 2 to the 4 over 16 minus 1 over 8 minus 1 over 16 minus a half. Evaluating these fractions give us a relatively nice answer to be 21 over 16 units. And this last example completes this section on arc length. Thank you.